Welcome to the Walton Pi. Today we are going to be talking about function composition. So to start off, let's define what it means to compose functions together. So if f is a function from a to b and g is a function from b to c, then the composition of g with f, often just pronounced g of f, which has the symbol being written as g little circle f, is the function from a to c given by g circle f of x is equal to g of f of x. So an example is if f is the function composed of pairs a, 1 comma a, 2 comma c, 3 comma c, and 4 comma d, and then g is the function of the pairs a comma x, b comma y, c comma z, d comma x, and e comma x, what is g of f? Well, we start by looking at where does 1 map to under f. Well, 1 goes to a, and then we look to see where does a go to under g. So a goes to x. So that tells us that we are going to have the pair 1 comma x in g of f. So by doing that for each of the other ones, we are going to get that g of f is the set of pairs 1 comma x, 2 comma z, 3 comma z, and 4 comma x. There's a few theorems involved with function composition, and one of the main ones that we get to use is the associativity of function composition, meaning that if we have 3 functions all composed with each other, it doesn't matter the order that you do them as long as you do ones that are next to each other. So h of quantity g of f is going to be the same as quantity h of g then of f. Those are all going to be the same. And so here is a proof of why that works. Because both of them are going to be functions from a to d, we just need to show that for any x in a, h of quantity g of f of x is going to be equal to quantity h of g of f of x. We have to show that that is true for any x. So if we go through and do that, it basically just turns into send everything down into h of g of f of x, and then undo what the definition of h of g is. So, as we have written out here, we can show that we are able to slowly break it down and then undo it to show that the two are actually equal. Therefore, the two functions are actually the same, so it doesn't matter the order that you associate the functions together with. There are also a few theorems involved with composing f with specific functions. One of these is if f is composed with the identity function, the result remains the original function f. Now, this doesn't matter which order we put it. So one case is if we do f of the identity. So that's going to be f of the identity of x, which is equal to just f of x because the identity function maps x to x. So we are going to get f of x. Our other case is if we are doing the identity of f then of x. So we are going to get the identity of f of x, which means that f of x just stays the same. Now, an important thing to notice is that these two identity functions in case 1 and case 2 are actually different functions because they are operating on different sets. In case 1, since f is a function from a to b, the identity function on x is going to be the identity function on the set A, whereas case 2, the identity function is going to be the identity function on the set B. So there are 4 more theorems that we are going to talk about briefly, but to start with all of them, we are going to assume that f is a function from a to b and g is a function from b to c. Our first theorem says that if g of f is injective, then f is also injective. So, think about this for a moment, and we will then walk through the proof momentarily. So our proof is going to be that if we start by assuming that g of f is injective and that f of a equals f of b. So that's how we start, and the reason we include the f of a equals f of b part is that is how we start any injective proof. we are going to now have to show that A must equal B. So, now that we have f of A equals f of B, we can take g of both sides to get g of f of A is equal to g of f of B. So that's going to be the g of f of A and the g of f of B. And since g of f is injective, that tells us that A must equal B, so that tells us that f is also injective. Our second theorem involving injective functions and composition is that if both f and g are injective, then g of f is also going to be injective. Think about this one for a moment, see if you can get the idea of a proof, and then unpause the video to be able to see one proof of this. So one way to prove this is to start by assuming that f and g are injective, and then assume that g of f of A is equal to g of f of B. Using the definition of g of f, that means we get g of f of A is equal to g of f of B. Since g is injective, that tells us that because g of something is equal to g of something, those two somethings, namely f of A and f of B, must also be equal. So then we have f of A equals f of B, but since f is injective, that tells us that A equals B, which is what we needed to show that g of f was injective. So that shows that if f and g are both injective, then g of f will also be injective. Our next theorems involve surjective functions. The first one is that if g of f is surjective, then g is surjective. Note that this differs from the injective theorem, because the injective theorem said that if g of f was injective, then f was injective. Here, surjectiveness implies that g is surjective, not f. So, think about how you might go about proving this, and then unpause the video to see one version of the proof. So we would start by assuming that g of f is surjective, and then we choose any element in our codomain of g. So choose any little c in the set C. Since g of f is surjective, and g of f maps A to C, that tells us that there is some little a in the set A where g of f of A is equal to our arbitrary C. That tells us that g of f of A is equal to C. Now, f of A is an element in B, because f is a function from A to B. So we have found an element in B which maps to our arbitrary C in our set C. So that tells us that our function g is surjective. The second theorem involving surjective functions is kind of like the last one we did with injective functions, where if both f and g are surjective, then we have to show that g of f is also going to be surjective. Think about this one for a moment, get an idea as to how you might go about proving it, and then unpause the video to see one example of a proof. One proof is to start by assuming that both f and g are surjective, and then to choose any c in our final set C. So, we need to show that there is some element a in our set A where g of f of little a is equal to little c. Now, since g is surjective, for any c, there is going to be some b where g of b is equal to c. And then since f is surjective, there is going to then be some a where f of a is equal to b. So, if we want to get c out, we are going to have g of b gives us c, but then to get b, we can get b by doing f of a. So we find that c is equal to g of f of a, so g of f of a will be equal to c, which tells us that g of f is surjective. Hopefully this video was helpful in helping you to understand composition of functions, as well as to see some theorems that are useful when dealing with function composition. If this video was helpful, please like and subscribe, it helps me out quite a bit, and feel free to check out some of my other videos. Good luck with all of your math, and have a great rest of your day.